Today we're going to talk about the second fundamental theorem of calculus, which is in chapter 6, section 4 of your textbook. So if you remember the fundamental theorem of calculus, we usually wrote it like this, that the integral from a to b of lowercase f of x dx is equal to capital F of b minus capital F of a, where f of x is the derivative, and capital F is the antiderivative, where you can think of that as the original function. And the other way you might have seen it was an f prime of x in the integral, and a lowercase f of b minus a lowercase f of a. Same thing. So, the fundamental theorem, obviously very important, that's why it's called the fundamental theorem. Fundamental theorem is helpful. We can use it to find an antiderivative, value of a function without actually having a calculator. So, what can we do if we're given an equation where there is no antiderivative formula? So, if you look down here, sine of x squared, and it says above, we can't find the antiderivative of any function that uses the chain rule. Can't find the antiderivative of any function that uses the chain rule to find the derivative. It doesn't mean that I'm not teaching you how to do that. It means you actually cannot do it. For example, sine of x squared. You cannot physically find an antiderivative of sine of x squared. But what you can do is use the second fundamental theorem of calculus to represent the antiderivative of sine of x squared. So you're going to use the original FTC, original fundamental theorem, but you're going to replace the a on the bottom with a 0 and the b on the top with an x. And then because we're using an x up top here, we have to use a different variable inside the function. So instead of writing f of x, we're just going to change it to f of t dt. So the second fundamental theorem tells us that this integral is equal to capital F of x minus capital F of 0. And so capital F of x really is the antiderivative. So if we want to represent just the antiderivative, we would solve for f of x. So we know that f of x is equal to the integral from 0 to x lowercase f of t dt plus f of 0. So you can use this to represent the antiderivative equation. So a capital F of x stands for antiderivative. And again, change the x to a t because you cannot have the same variable on the top of the integral as inside the integral. They have to be two separate variables. So in general, the second fundamental theorem says if a function is continuous on an interval and a is any number in that interval, then you can write an integral from a to x. So the only difference here is we're not putting a 0 on the bottom, we're just putting an a. And again, we have to use f of t dt plus capital F of a equals capital F of x. And again, this is just a general way of writing an antiderivative. So any antiderivative can be found by using the second fundamental theorem. Basically, the only difference is there's an x on the top, a variable on the top, instead of a number b on the top. And this is going to be really handy when you're given an equation where you can't solve, again, you can't find the antiderivative using a known formula. So let's go back to our sine of x squared. And they're telling us that f of 0 equals 3. Find f of 4. So because 0 is less than 4, 0 is our a, and 4 is our b. So this is really... This part 1 is actually a regular fundamental theorem because they gave us a 4 here, not an x. So we would say f of 4 minus f of 3, f of 0 is equal to the integral from 0 to 3 of lowercase f of x dx. Okay, so we know that f of 0 is 3. And then for this integral, you would just have to put this in your calculator. So the integral from 0 to 3 of f of x dx, when you put this in a calculator, gives you 0.774. Actually, correction, that should be 747, sorry. And so then to solve for f of 4, we just add the 3 to the other side, and we get 3.747. So that's just plain old FTC like you're used to, like we did back in chapter 5. And same thing with part 2, because again, they gave us a 0 and a 2. So 0 is our A, and 2 is our B. So we would do f of 2 minus f of 0 equals the integral from 0 to 2 of e to the negative x squared dx. And again, e to the negative x squared, if you were going to think about taking the derivative of that, you would have to use chain rule. And so this is, again, an integral you could never solve by hand. You can only solve in the calculator. So we know that f of 0 is 5. And if you plug this one in the calculator, you get 0.882. And so then when you add the 5 to the other side, f of 2 is 5.882. So now in example 3, this is where the second fundamental theorem comes into play, because they're giving us a 3 here, but an x here. So x is always going to be like your b, and so the value they give you is going to be your a. So to represent g of x, you would do g of x minus g of 3 equals the integral from 3 to x, and then again, this is where it's really important that you change the variable, because there's an x up top. You can no longer have an x inside the integral. So I'm going to write t squared. You don't have to use t, but that's generally what people use, dt. And then I'm just going to solve this for g of x, because it says find g of x. So g of 3 was negative 2. So I actually had a minus negative 2 here, which made a plus 2, but then when I move it to the other side, I'm back to a minus 2, plus the integral from 3 to x, cosine of t squared dt. So we have a formula for the antiderivative, even though we can't find the actual equation. We can use this formula to find values of the antiderivative. And again, cosine of x squared is something we would never be able to find an equation for, but we can still find antiderivative values using the second fundamental theorem. And just one quick little note, if the x is on the bottom, right, it should be on the top, right? And this doesn't have to be 1, it could be any number. You want to flip it. You want the x on the top, just like with any integral. You want the b on the top, but when you flip it, it makes it negative. So make sure you put that negative sign out front. Okay, so what happens if we take the derivative of an integral? Remember, d dx means derivative, and then integral basically means antiderivative. So if you take the derivative of the antiderivative, they should basically cancel each other out. They're opposite functions. So the derivative and the integral cancel each other out, and the dt is part of the integral. So you're only left with sine of 2, but the only thing you have to keep in mind to do is actually, because this is the derivative with respect to x, and there's a t in here, we're going to put this x back in. So it's the sine of 2x. So the derivative and the integral cancel each other out. You just have to remember to change the variable back to that top variable. So for this one in number 2, we're just going to plug that x back in, and we get e to the negative x squared. Now in number 3, this says x squared here, okay? So if I'm going to find the derivative, I'm still going to plug this back in. So I'm going to get the sine of x squared, but I have to think chain rule. and I have to multiply by the derivative of the top. So the derivative of the top, this x squared, is 2x. Anytime you do a derivative, you have to think chain rule. Up here, when I'm plugging the x backs in, the derivative of x is just 1. So technically I was multiplying by a 1 up here. I just didn't need to write it down. So same thing with number 4. I'm going to take this x cubed. I'm going to plug it in where I see t, cosine of x cubed. However, I have to multiply by the derivative of x cubed. And again, that's straight from the chain rule. So times 3x squared.